Alright, well, as you can see, my name's Matt Osman. I go to college in Illinois, at Augustana College. I also live in Illinois. I'm a junior geology major, and I am really excited to be up here. It's flat in Illinois, yeah. So we're going to talk a little bit about isotopes. What are isotopes? Isotopes are more or less stable variations of water molecules. And what it amounts to actually is that these things end up heavier than normal water molecules. And they're found in trace amounts, just enough that we can measure them. And I guess I'll just go ahead and point out that they're heavier just because each one has an added neutron. With O18 has 2 added neutrons. And O18 is actually what we're going to concentrate on. Don't bother with the H2O17. That is the loser molecule that we're not going to pay attention to. Alright, so fractionation is a kind of fancy word, but it's a basic process actually. What happens is water evaporates out of the ocean, and amounts that are pretty well measured. We know them pretty well. They're known as standards. And as they move inward, the heavier stuff preferentially falls out. And we can measure this along the path, and it's pretty quantified at this point. So you get a depletion as you go further inland. So, come on. All right. So we want to study these things because they tell us a lot about the water transport in the global scale, in a regional scale, and a local scale, blah, blah, blah. They also tell a lot about temporal correlations. And that's actually the most important thing. It's really cool that they can do this, and because of that, it's used for past climate, figuring out past climates. I added this picture here, the ice core, because that's actually that's why we core. We look at these O18 and deuterium values so we can figure out these past climates. And this is done a lot in Antarctica and Greenland. We read about it a lot. And it's really cool, but there's actually a problem with this when we do it in a lot of locations. And that's because we don't actually understand everything in the world. And that's actually not a stab at science, because a lot of times we use models to figure these things out because there's not enough scientists to go around and figure out how these things are occurring in nature. So we have to inference a lot of these areas. And while this works in the Arctic a lot, it doesn't actually work in a lot of areas that have complex climatic regimes and high elevational relief. And one of these areas, obviously, is the Juneau ice field. So that brings us to my study. We're looking at the fractionation parameters along the Matheson and Llewellyn, which has been brought up a few times, so it's pretty familiar at this point, I'm assuming. And we looked at about 40 kilometers on this. And it's a cool area. It has about 2,000 feet of elevational relief, which is going to have some hopefully cool implications added to that. And because this is also a plausible future site for drilling locations, which hasn't been done a lot in the Juneau ice field, so it's a really cool spot to be studying. So for the procedure, we went along this transect that we created, the 40-kilometer one, and at each kilometer, and then around the divide at each half kilometer, we took 3 samples, and they were just surface snow samples, so we didn't dig down too far. I had down there, we had 2 at 10 centimeter depth and 1 at 20 centimeter depth. And with doing something over and over again, you get pretty good at it, and we got it down to about 3 or 4 minutes in between the points, so that was pretty cool. But once we got those, we took it to our impromptu ice field laboratory with the machine that Jeff showed earlier that we're really lucky to have. And there we did another repetitive process of melting down the samples. We took little syringes, 1 microliter, which is just a tiny little droplet, put it into the machine, it spits back a whole bunch of numbers. We do this about 7,000 times. And then we get a whole bunch of numbers, which we play around with. And if everything turns out cool, we get a nice looking graph. Yeah. This didn't show up the last presentation we got, so you guys are seeing it all now. So it's a pretty distinct depletion trend here. And you can think of that x-axis, I have it as sample number. You can also think of that as, with a higher sample number, it's also going up in elevation. So as you go up in elevation, you get a depletion. This is what we'd expect, because as you go up in elevation, it gets a little colder. When it gets colder, these water molecules condense. More rains out, the heavier stuff rains out. We get a depletion. It can also mean a number of other things, which I'm not sure about yet, and either or others. So I suppose that brings us to future work, which is deciphering why this is occurring, obviously. We're going to use some models for that, see if the models line up. We're also going to obviously finish analyzing the points because that's only half the data. What I showed you was the math. I also have to do the Llewellyn. I will state that I started doing it a couple days ago and it looks pretty good too, so pretty excited about that as well. But that's where we're at right now, so I want to throw out some things. That's my partner in crime for the whole summer, Bradley Markle. He was my advisory assistant, and he was awesome. Thanks JIRP and all you guys are awesome. Augustine College NASA for funding, and the University of Washington for the isotope machine. And that should be it. Thanks, guys.
Questions for Matt?
All right.
Okay. Next, Zach Miller, talk about, please, testing the variability of isotope samples as a proxy for temperature on temperate glaciers.
Alrighty. I'm Zach Miller. I grew up in Juneau, moved to Anchorage about 5 years ago. I go to West Anchorage High School. Now I'm Dr. Maynard Miller's grandson. Haven't started an ice field research program yet, but we'll get there. So, testing the variability of isotope samples as a proxy for temperature on temperate glaciers. Why would you want to do that? Well, as Sasha kindly reminded us, we all drink water. And if water melts off glaciers, you can drink it, or you can use it for hydropower, as we do in Juneau, or like various water resources. So using isotope samples for a temperature proxy, you can estimate the temperature on glaciers and guesstimate how much they're going to melt, which is very important. Yes. Yeah. We're just giving up on this one. Okay. This is a little refresher. It's been a long time, so. It's actually sort of relevant just to get the idea of. I actually used deuterium instead of oxygen-18 because I wanted to be difficult. So what did I do? Well, I didn't really do anything. I had most of my field work done for me by other people, which is what important scientists do. Here's a picture of someone that's not me sampling a snow pit. And people that weren't me sampled every 50 centimeters down. So what we were hoping to see is, you can see an ice lens there. So like below the ice lens, as the water comes down the snowpack, and then it stops at the ice lens and it refreezes, and that's meltwater or rainwater from the surface. So we were hoping for more consistent results right below the ice lenses. That's not what we found. This is the area of study. This is Juneau, as you can tell by the font. And then the ice field, Atlin, is where I studied. We'll zoom in, map. These are the two locations, the nice red dots, which I don't have one of, but it's there. And there's the other one. So, didn't update, okay. This is the first pit. So as you can see, I was disappointed when I saw that these are not in a nice straight line. This is the distance below the snow surface. So if this is the surface of the glacier, this is the annual layer down here. And then you can think of the horizontal axis is basically the variability between, we ran each sample at each depth multiple times, and that's the standard deviation, or essentially the variability between the test runs. Yeah. Here's the next pit. It was up there. The other one's down here, closer to Juneau, closer to home. And then we put them side by side and saw that there's this cool, nice little correlation here. Instead of there being low variability below the ice lenses, that's what these lines are, there is this rise at the surface, so it's variable, which even makes sense because there's rainwater and meltwater from different storm systems at the surface, and then as you go down in the spring, it's less variable, which was surprising. We can guess that as the water percolates down, like it blurs the snowpack together, so it's actually going to be less like representative of the system, of the snow at that level, because it's actually just like a combination of all this water. And then in the winter there's less melt, so it's more variable because of wind, reposition, or whatever happens in winter. We're not really sure. So, future work. Well, I took some rainfall samples to test the isotope, the actual accuracy of the machine, and then I actually did do some field work. I lied earlier when I said I didn't do anything. But there were malfunctions with the machine, and so we're running those now, and then those are at higher resolution, so hopefully we'll be able to see better correlation there. Yeah, so I have a lot of work to do, pretty much all my work to do, but that's an idea of what I have done, or haven't done. But thank you. Hey, questions?
Yes. Do you see an increase in isotope percentage as you went down?
Hmm?
Do you see an increase in isotope percentage as you went down into the ice?
Down.
Into the snow?
So there's the winter snowpack, then there's the fall where there's more melt, which I forgot to address. It's kind of similar to the spring. And then down here is the surface from the last year, so it's an increase again. Does that answer your question? Sorry?
A little bit, because you're showing variability, right?
Mhm.
Variance in ozone,
Yeah.
but not isotope as like a percentage of, not the isotope percentage?
Yeah, that's actually a different thing
Yeah.
to study. This is basically just the accuracy. So if you were to, probably should have addressed this earlier, but if you were to drill an ice core, you would like to see the temperature at each one of those levels, each season or each year, the average temperature. And I'm essentially testing like if that temperature that you found from the isotope would be accurate for representing what the temperature was at the time of precipitation. And so it's going to be very unrepresentative in the winter, and then more representative, you could argue, but it could also be because of rain, so we have to do more work on that. Thank you.